Frequency is what's given as 20 rotations per second, from which you find the angular velocity, 2 pi f, 2 times 3.14 times 20, 120.6 rad per second. Then find velocities r omega or omega times r to get 120.6 times. I realized I made a mistake in the calculation, so I corrected it to 125.6 times 0.16, so the answer is 20 meter per second. So first we had to realize what was given was the frequency, right? Find omega, use that. So here's the answer for number 2. Radius is 1 meter. Angular speed is omega, that's 2 rad per second, and you have to find the radial acceleration or the centripetal acceleration, for which the formula is v squared by r. I believe that's the formula given on your formula chart. Right? That's why I put that first. But there's also another formula that says that velocity is omega times r, isn't it? Isn't that one there on the formula chart too? So you got to substitute that here and get a new formula out of those two, which will be omega squared r squared by r. Because when you substitute that in place of velocity here, that's what you're going to get.
So centripetal acceleration is the
Radial acceleration. Centripetal acceleration is also called radial acceleration. It's along the radius towards the center, isn't it? So the r's get cancelled, 1 r rather, and then you have omega squared times r, plug in the number, you get 2 squared is 4, that's why it's 4 times 1, 4 meter per second squared. So once again I'm writing that formula to show you that you need to get that formula for radial acceleration, which is omega squared times r. So once you get that, that's your answer. So on number 3 now, alpha, that's the acceleration, 4.5 rad per second squared. Initial angular velocity is 1, that's omega naught. You have to find theta. Delta t is given as 2 seconds, and the equation is theta is omega naught t plus 1/2 alpha delta t squared. Plug in the values. First term is 2, the second one is 9, and you get 11 radians as your answer. So that's the angle through which it turns. On number 4, the diameter is 68 centimeters, so the radius is 34 converted into meters, right? And the initial velocity is 8.4 meter per second. And what's the final velocity? 0. Okay, so the final velocity is 0. And it says it covers the distance of 115 meters. So all that is given, and you have to find the alpha. So like I said, alpha is A divided by R, very important. And then first we use that equation, V squared is V naught squared plus 2A delta X, rearrange. You're trying to get A from there. Plug those numbers given. So once you get that, you got your linear acceleration, right? From there, plug it back into this and find the angular. That's it. So 0.31 by 0.34, which is, that is negative 0.91 radian per second. 91, the answer key shows 90. That's how you do it. Here is number 5. Wow, that's a good diagram, isn't it? Okay, 4 meter, showing you the original position and after it is rotated. First, calculate the rotational inertia or moment of inertia as 5.33 times the mass. 4 squared is 16, obviously, and you get 5.33 times the mass because the mass is not given in the question. And then torque is R times F. That is 2 because the mass is assumed to be concentrated at the center of gravity. So although the length is 4 meter, you take the radius as only 2. So 2 times mg, that's 9.8 times 2, 19.6, and then use the other formula for torque, which is I alpha. Rearrange. Alpha is tau divided by moment of inertia, and the masses cancel out, you get your answer. 3.68 radians per second squared. All right, number 6, here is the diagram. That's the disk. That is the mass that is hanging there, 1.53 kilogram. The force is mg, which is 1.53 times 9.8, gives you about 15 Newton. And then torque is R times F, so 0.66 times 15. It's 0.66 because you have to change the centimeter into meter. So you get 9.9 meter Newton. And then the moment of inertia is mr squared by 2. .07 times 0.66 squared divided by 2. Okay, that is where I had to add something. Look at that. That is the moment of inertia of what? Of the disk. Is there anything else here that has moment of inertia? Rope? Oh, we did not even consider the mass of the rope, right?
No.
Actually, you have to, but it's neglected here. But this,
No.
the hanging mass also has moment of inertia. I forgot that, so I had to bring it down. So you have to find the moment of inertia of the mass, which is mr squared. Because for a particle, it's mr squared, isn't it? So 1.53 times 0.66 squared, which is the quantity that I first missed. Therefore, you take the total of the two, add them up, and then use alpha is tau by I, which is 9.9 divided by 2.2 gives you 4.5 radians. That's the answer. Oh. Number 7. That's the kinetic energy. Angular velocity is given, 400 radians per second. Formula is 1/2 I omega squared. Rearrange, you get I is 2e by omega squared, 2 times 1 times 10 to the 6 divided by 400 squared. That gives you 12.5 kilogram meter squared. Take note of the unit, kilogram meter squared. That is the moment of inertia. So on question 8, that is the inclined plane where the sphere rolls down. And actually the height of the inclined plane is given, isn't it? So at top, where I have written it as point A, what kind of energy does it have at A? Potential energy, and as it rolls down, it gets converted into kinetic energy. So that's the basic idea. So potential energy at A is equal to kinetic energy at B. But remember that the kinetic energy at B is of two types, both rotational, given by 1/2 I omega squared, and 1/2 times mass times velocity squared, which is translational. So the potential energy at the top becomes the total kinetic energy at the bottom. And then you put in the numbers that are given. And again, you have to first find the moment of inertia of a sphere. That's not on your formula chart, is it? So that's something you'll have to remember. Two formulas. mr squared by 2 for a disk. For a sphere, 2 by 5 mr squared. And of course, for a particle, it is just mr squared. So 3. For a disk, it's 1 by 2 mr squared. For a particle, cylinder is the same as disk. For a particle, it is mr squared. That formula, I think, is on the formula chart, mr squared. And then for a sphere, solid sphere, it's 2 by 5 mr squared. So first find it, 2 by 5 times 1 times the radius squared. And you get that as 4 times 10 to the negative 5. So mgh is 1/2 times. You know, I decided to plug in all the substitutions before I put in the numbers. That's why I changed it. Hold on one second. Here, do you notice that here I've used omega is V over R? See that? And substituted there. And then what I did here is I brought the 2 onto this side. So that's why the half on the right side becomes 2 on the left side. And also I took out velocity squared as common factor. You really need to, you see the velocity squared? There's both in these two terms, you have those. So that's taken out. That's how I got that formula. And then I plugged in the numbers. Simple math, take the square root of 14 and you get 3.74 meter per second. Once again, note that this is 0.01 squared, okay? 10 to the negative 2. That's why it's 10 to the negative 4. It's radius squared. Okay, number 9. It's a hoop. So the moment of inertia is mr squared. You can find that. So 0.05 kilogram meter squared. Once again, potential energy at the top is equal to total kinetic energy at the bottom, isn't it? That thing didn't change. It's the same thing. The only difference is, now that's again the same. Omega is V by R, so square it. Take out velocity squared is common. No difference there. Now, it's the same thing. And so it's 2 mgh divided by I by R squared plus mass. So plug those numbers in. Get 11.76 divided by 0.4. First find that out and then take the square root. 5.42 meter per second is the answer. So on number 10, you have to find the radius. Density, rho, is mass by volume. Volume is 4 by 3 pi r cubed for a sphere. So when you substitute into the formula for density and rearrange, the 3 goes to the top. So you have 3 times the mass divided by 4 pi r cubed. Make r cubed the subject. Get 3 times the mass by 4 pi times density. Mass is 6 kilograms. And the density is given as 5,000. So you get r cube is that number, really small. You got to take the cube root of that. Cube root of that number gives you the answer, which is 0.065 meter. Because the answers are given in centimeters, multiply that with 100, 6.59 centimeter. That's number 11. The torque is change in angular momentum divided by time, so that's 20 divided by 4, 5 meter Newton. Here is number 12 for you. That's the diagram. From the fulcrum, the load is 1 meter away, and the worker is applying a force F 4 meters away from the fulcrum. And the force applied is given as 400 Newton. So if you take the torque about this point, what will you get? About the fulcrum, which is the counterclockwise.
No.
400 times 4, isn't it? So the weight of the lever need not be considered because it's not given. Is it given? So compared to the others, it's negligible. That's why. So 400 times 4, that's the counterclockwise, is equal to the load times 1. That's it. So 1600 Newton. Yeah, just remember that the total downward is equal to total upward. So the total force on the fulcrum would be 2000 Newton. All right, obviously on routine, this is the diagram. 500 Newton and 350 Newton. And you have to find the position of the 350 Newton child. The question is, do we even have to consider the weight of the board? Why not? Yeah, you take it at the fulcrum. So the torque due to that is 0, isn't it? That's why. And therefore, 350 times x is equal to 500 times 1.5. So x is 750 by 350. 2.14 meter. As simple as that. Number 14, here is it. Okay, 500 Newton person stands there, and the weight is 100 Newton. I must have shown it a little bit smaller anyway. Isn't that what the question says? 500 Newton person. And there are two support forces, F1 and F2. And we know that the total up is equal to total down, so F1 plus F2 should be 600, isn't it? Yeah. F1 plus F2 should be 600. And what else does the problem say? It tells you that the support force at the right end is 3 times that at the left end. So how will you connect F1 and F2? F2 is 3 times F1. That's the next step. So if you put F2 is 3 times F1, so you would get F1 plus 3F1 is 600, which is 4F1 is 600, so F1 is 150. Yeah. Okay. And then you take the moment about one of the supports. Yeah, I took it about the right one. if you take it about the right one, you have 2 counterclockwise, isn't it? And 1 clockwise. The 2 counterclockwise would be 500 times x, and the other would be 100 times 4, because it's 8 meters. Yeah, so 500 times x plus 100 times 4 is equal to F1 times 8. F1 is 150, so put that down. Simple math. So you get 500x is equal to 800, and x is 800 divided by 500, which gives you 1.6 meter. 15. The length of the cable is 100 meter. Area of cross section 1 millimeter squared. You have to be careful there. Do you remember how to convert millimeter squared into meter squared? If you were to convert millimeter into meter, you would divide by 1000. But I told you have to divide by 1000 times 1000. That will make it dividing by 10 to the power 6, which is multiplying by 10 to the negative 6. Okay, anyway, when I write that down, force is 1000 Newton. Young's modulus is 1 times 10 to the 11, and the formula for Young's modulus is F by 8 times length by change in length. Make change in length the subject. Rearrange, substitute those numbers. And then that's what I'm showing you, how to convert the millimeter squared into meter squared. Did you notice? That is dividing by 1000 times 1000, okay? Which is dividing by 10 to the power 6. So it's multiplying by 10 to the negative 6. Get used to that. So 10 to the negative 6 times 100 divided by, which gives you 10 to the 5 divided by 10 to the 5, 1 meter. On 16, the length is 4 meter. The radius is 1 meter, 0.1 meter, because the diameter is 0.2. Take half of that. How do you find the area of cross section? Circle by r squared. Find that. Get 0.0314 meter squared. And then use the formula. That's the Young's modulus. You have to find how much it shrinks. Excuse me now, length. .12 times 10 to the negative 5 meter. $17. Now that's the diagram. When it talks of shear, you know that it's a tangential force. You are asked to find the relative displacement, so that's x. You're looking for x, isn't it? Right? And there theta is going to be x divided by the length. Now, G is the symbol for shear modulus, and it's F by A theta. Make theta the subject. F by AG, 400 by 0.3 squared. Because each face is a square, isn't it? And the area of a square is A squared. So, and then after you get theta, use x divided by the length and make x the subject. 1.78 times 10 to the negative 7 times 0.3. So you get 5.33 times 10 to the negative 8 meter. So that is the change in pressure. Bulk modulus, that's the formula, but sometimes you see it given as how? Delta P, is it? Change in pressure times volume. So change in volume, rearrange that. Change is 10 to the 7 times volume is 1 meter cube, and the bulk modulus is 2.3 times 10 to the 9. Wow, so easy. So 19, the pressure is maximum when the area is a minimum. Yeah, that's what I wrote. Pressure is force divided by area, and the minimum area in that one is, of course, which one? 10 times 4, isn't it? But that's in centimeter squared. You have to change it into meter squared. Ooh, very good, I stopped it right on town. Tell me, how do you change centimeter squared into meter squared? Again, how do you change centimeter into meter? You divide by 100. 100 times 100. So that will be dividing by 10 to the 4, or multiplying by 10 to the negative 4. Yeah. So multiply by 10 to the negative 4. So pressure is 50 by 40 times 10 to the negative 4. So 1.25 times 10 to the 4 Pascal. And the answer is given in kilopascal, so I wrote it as 12.5 times 10 to the 3, which is 12.5 kilopascal. Right? Because 1,000 pascals is 1 kilopascal. So I had to write it as 1,000 there. I just moved one decimal place here and put this as 10 to the 3. Did you get that? I divided by 10 and multiplied by 10. That's what I did. So 12.5. Here is number 20. For you, pressure is force by area. The force is given. How do you find the area? Pi r squared, yes. Area is pi r squared. Radius is 15 centimeter. Change it into meter. It will be 0.15. So you get 0.07 meter squared. So divided by that area, you get the pressure as 73.60 Pascal. Then the question says, what maximum depth can you take it, isn't it? So once you get the pressure, you have to use P is equal to H rho G and make H the subject. So it's pressure divided by rho G, that is 73.60 divided by, that's a mistake I made there. Do you notice? The density is 1,025 somewhere along the line, and I got 700 and I changed it. So I changed it to 1,000 because it says in a lake. So that's 750 meters. So this is 21. Big force by big area is equal to small force by small area. So you're asked to find the bigger force, rearrange, plug in the numbers, and you're done. 500 times 20, that is 10,000 Newton. Amazing. Just by applying 500 Newton, you're getting 10,000 Newton. 22. The resultant force or the tension is the weight take away the buoyant force, isn't it? And what's the formula for buoyant force? You need that on the exam. at least a couple of times. Formula for buoyant force. Anybody? Volume of the fluid times density of the fluid times G. That's on your formula chart. Buoyant force is always volume of the fluid displaced times density of the fluid times G. And in this case, the volume of the fluid will be the volume of the ion. Why? Because the whole thing is underwater, isn't it? And how do you find the volume of the ion? Mass divided by density. What is its density? It's not 7.86. That's the specific gravity multiplied by 1,000. So its density is 7860. So you see that there, 4 divided by 7860. Whenever the specific gravity is given, multiplied by 1,000 to get the density. Alright? So the specific gravity of water is 1, its density is 1,000. The specific gravity of iron is 7.8, its density is 7860, and so on. So you get that as 5.08 times 10 to the negative 4 meter cube. Use that to find the buoyant force. Volume of fluid times the density of fluid is 1,000. That's 10 cube. So, and I got it as 4.98 Newton. So the tension is the weight, which is 4 times 9.8, minus 4.98. 34.22 Newton. That's the tension in the string. Memorize. All right, 23. Volume of the box. Length times width times height gives you 2.5 meter cube. And so, actually it's asking for maximum mass. I don't know, I put it as weight of fluid is VF times rho F times G, correct? Okay, so 2.5 times 1,000 times 9.8. Probably I just wanted you to remember that formula like that. So I got it in newtons, but since they're asking for mass, I got to divide that by 9.8. So the mass of floating object can only be that much, which is 2.5 times 10 to the 3 kilogram, because I divided that by 9.8. Divide 24,500 by 9.8, I would get this answer. Okay, so that's the diagram. The weight is 200 kilogram plus the weight of ice, isn't it? Right, both. Weight of ice. So you're asked to find the area, so we go make weight of ice the subject. The weight of ice is given as volume of ice times density of ice times G, which is area times density. Okay, area times height, actually. Area times 1 is the height, because area times height gives you volume. Correct? 8 times 1 gives you volume, and then volume times density is 980 times 9.8, and you get 9604 A. So the weight is now 200 times 9.8. I had to multiply that with 9.8 plus 9604 A. That's the total weight. That is 1960 plus 9604 times A. All right, what's the weight of fluid displaced? Again, for the umpteenth time, volume of the fluid times density of the fluid times G. Volume of fluid is 1030, and get it as 10094 A. So 1960 plus 9, equate both, they should be equal to each other. Because if something should float, the weight of the floating object should be equal to the weight of fluid displaced. So equate, now it's only math. Collect those two terms that have A's in them. You see two terms. This one has an A, this also has an A. So take that difference, 490 A. So A is 1960 divided by 490, which is 4 meters squared. So if that ice floe has an area of 4 meters squared, this polar bear will still be alive. 25. That's the equation of continuity. A1V1 is equal to A2V2. Use that first. Where did I get that 12A1? Doesn't it say in the problem that the area of cross section is 4 times? It doesn't. It says that the radius is twice, isn't it? If the radius is twice, then the area is going to be 4 times, because it's pi r squared. 2 squared is 4. So that's why the A1s cancel out. So I get that the velocity is 3 meters per second in the wider region. Okay. Now we got to find the pressure using Bernoulli's equation. And remember, if it's a horizontal pipe, you cancel out the potential energy quantity, right? You only have pressure energy and kinetic. That's the formula. It's on your formula chart. Rearrange to find the pressure 2. And you can find what I did there. Just took these two quantities. Took 1/2 rho common. Plugged in the pressure. It's given us 3 times 10 to the 4 plus 1/2 times. The density of water is 1000. That's 12 squared minus 3 squared, 144 minus 9. So I get second term is 67,500. Add the 2, you get 97,500 Newton per meter squared, or 97,500 Pascal. That is the pressure in the wider section. Thank you.